So if you agree, we can go on and proceed with the last presentation. It's from Miroslava Kredl from Crane Institute. You can take the floor, please. Please.
On my report, I would like to discuss some peculiarities of bond strength degradation in reinforced concrete. So reinforced concrete structures are long-term operated objects with a service life up to 100 years. During their service, they are subject to service loads and also to ambient effects, such as static temperature changes, acid rains, pollution with de-icing salts, and so on. All these factors can influence the structural integrity of the composite and leads to worsening of its serviceability. One of the main reasons of properties worsening of reinforced concrete is bond strength degradation between reinforcing steel and concrete cover. And it could be caused by two different factors, reinforcement, corrosion, and overprotection of concrete. So, corrosion of reinforcing steel is one of the main reasons for reinforced concrete structure deterioration. Accumulation of corrosion product as a steel concrete interface, which volume is larger than the original iron volumes, lead to creation of internal stresses at the interface, and this promote cracking and spalling of concrete cover. Example of this effect you can see on this slide. Cathodic protection of reinforced concrete structure is commonly accepted practice for reinforced concrete installation, for example, for bridges, and it is efficient for corrosion suppression in reinforced concrete, especially when an installation is operated in chloride-contaminated environment. However, during cathodic polarization of steel reinforcement, hydrogen can generate at the concrete surface. The role of hydrogen in structural integrity of reinforced concrete usually is reduced to consideration of hydrogen embrittlement of steel reinforcement. However, it is well known that only a tiny part of hydrogen electrochemically generated on the steel surface can penetrate metal, and the most of hydrogen recombines and evolves a gas at the steel surface surrounded by concrete. And it seems to be important to analyze the role of just this hydrogen on steel concrete interface and on concrete itself as well. Both about mentioned effects which could cause bond degradation in reinforced concrete could be simulated in laboratory conditions by respective electrochemical methods, namely application of impressed anodic currents accelerate corrosion, and cathodic polarization can simulate overprotection of concrete. So here we can see the scheme for our electrochemical installation for electrochemical impact on the specimens. In our work we used two types of reinforced concrete specimens. The first is a high concrete cylinder with a smooth reinforcement. Place it axially. For accelerated corrosion test, these specimens was fixed in a framework made of stainless steel, which served as a cathode. Current was applied to the specimens using power supply. We maintain constant voltage of different values, and corrosion current was measured during the experiment. For the assessment of stress, bond stress changes in reinforced concrete, we use another type of specimen. It is a short concrete cylinder with two rods of different lengths with the insulating gasket between them to prevent their electric contact. And in this case, for hydrogenation of this specimen, the longer rod served as a cathode, and in this case, auxiliary electrode anode was platinum wire. And in general, the scheme was similar, so only polarity of power supply was changed, and auxiliary electrode was replaced from this stainless steel to platinum. Concrete composition for specimens preparation and casting procedure were the same for both types of specimens. Specimens were prepared using type 1 portland cement with water to cement ratio equal to 0.5, and also sand and gravel was added as fine and coarse aggregates respectively. So let's go to the results of accelerated corrosion tests. So as I have said, we used constant voltage of different to provide different intensity of corrosion, and the main observation are the following. Under the most intensive polarization, the most intensive corrosion occurs, and the shortest time is needed for cracking. And the higher voltage, the less amount of corrosion products is required for crack appearance. It is known that not all corrosion products exert expanding pressure at the steel concrete interface. Some corrosion products can fill pore and defects in the near concrete layer, and some of these products can also migrate into the bulk of concrete. Evidently, under low corrosion rate, corrosion products have much time to penetrate into concrete, hence the critical pressure required for crack formation is attained under a large amount, under a less amount of when corrosion is low, that we have more corrosion products, and when fast corrosion, the corrosion product is low. We concluded that under moderate polarization, more adequate results of simulation should be achieved. Here is example of broken specimen out after our experiments, and interesting peculiarity was revealed. Usually the depth of corrosion product penetration into concrete is only several millimeters. It was shown by many researchers. But in the present study, deep penetration of corrosion product is revealed. Corrosion products seems to be distributed not only in the near surface layer in concrete defects, but also in unbroken concrete matrix. It could be explained by the formation in the course of corrosion soluble species. In the presence of chloride ions, it is green rust, chlorocomplexes, so-called green rust, which can diffuse through the concrete cover away from corroding steel, and this breakdown in oxygen-rich areas closer to the lateral surface of the specimens to form solid ferrous compounds. This results in corrosion products being distributed in the whole concrete paste. But question remains whether rust, which is present in significant amounts in the concrete paste, could create internal stresses which could influence the structural integrity of the installation on the whole and leads to worsening of their serviceability. The next part of this work is the results of Pullout test after impressive cathodic current. We can see the broken specimens example as in the previous type of test, and interesting observation was that when we test the specimens which were not undergone hydrogen charging, they always shorter rod withdrew from the specimen during loading. And when we test hydrogenated specimens, just hydrogenated rod withdrew despite it was longer. Bond stress values in the range of several MPa is typical for smooth reinforcement, while the values for hydrogenated rod were enormously low. In spite of data scattering, conclusions could be drawn that bond stress is essentially lower for hydrogenating specimens. So it indicates the essential bond weakening due to hydrogen charging of the specimen. It should be noted that during cathodic polarization, chloride ions moves from the reinforcement, while potassium and sodium ions move toward the reinforcement. It is phenomenon of electromigration. And it's shown by several researchers that rising concentration of these cations near the interface leads to softening of concrete paste. So under such conditions, we should achieve losing of bearing capacity of reinforced concrete. However, on the other hand, hydrogen charging of this steel should not be neglected, because even under acceptable level of cathodic current, existence of some overprotected areas is eventual due to non-uniform distribution of protecting currents in the reinforced concrete. Hydrogen bubbles were observed visually during the experiment on the lateral surface of concrete and also at the top face in the place of contact of steel and concrete. Designating two ways for hydrogen to release from metal. Therefore, hydrogen moves from the interface upwards along the reinforcement and also through the whole concrete cover. And the question is whether its movement is equilibrium or it accompanies by creation some stresses, internal stresses in concrete matrix, which could later influence the structural integrity of this composite. When hydrogen moves upwards, it could destroy partitions in near concrete near the reinforcement, and also it is a way for weakening of bond strength in reinforced concrete. So under cathodic polarization, adhesion disturbance in reinforced concrete specimen could be caused not only due to electromigration, but also as a result of hydrogen evolution at the steel surface. And some conclusions I will read because I think we have time. Intensive dissolution of the reinforcement embedded in concrete under not electrochemical conditions leads to reinforced concrete specimens cracking, which could accompany by their extensive filling with corrosion products. In this case, concrete cover cracking is delayed because spreading of concrete products suppresses potential rise of their expanding pressure near the interface concrete reinforcement. However, essential outflow of corrosion products from the interface could weaken bond strength by the way of stresses formation in the concrete matrix. A prolonged application of cathodic compressed current caused bond degradation, bond strength degradation in reinforced concrete. The reasons of the bond weakening could not be only electrochemical processes in concrete such as ion migration, but also hydrogen evolution at the steel concrete interface. Special attention should be paid to possible impact of stresses produced in concrete by hydrogen moving outwards from the interface through concrete matrix, which allows superposition of hydrogen-induced cracking in concrete. Thank you for your attention.
Okay. Thank you very much for the presentation.